Hi, Arvind Kumar from IBM Research, and I wasn't sure if a title like this would attract people or scare people off, so I'm not. I'm glad to see that there are a lot of people here. So, essentially, what I want to highlight today was some of the real challenges in trying to produce chiplets for an open chiplets ecosystem, or eventually to be part of such an ecosystem, and some of the particular challenges that we've been facing. So as an outline, I'll start with just an overview of IBM's AI hardware journey, talk about chiplets and the open ecosystem, and then I'll try to give a perspective of what it's like if you're an AI chiplet out there and you're looking for partners and mates and some of the particular challenges you might be facing, and then what can we do about it as a community, as a call for action. So let me start with a recent announcement, which is IBM Spire AI accelerators. You might be asking, well, there's so many accelerators, AI accelerators out there, and GPUs. You know, what's new or unique or special about this? So the specific problem that is addressed by the IBM Spire AI accelerator is for enterprise customers, which have been traditionally the bread and butter business of IBM. And enterprise customers like banks, big governments, airlines have very unique enhanced requirements for generative AI cases. This includes things like enhanced security, enhanced automation, and enhanced fraud detection. So this is an AI accelerator which has been designed with their needs in mind. It has been taped out, as you can see on the right side, in the form factor of a 75-watt PCIe Gen 5 by 16 adapter. The chip that you see there on the bottom is an SoC with 32 AI cores. It's a 330 square millimeter chip with 26 billion transistors, and it was taped out in Samsung 5 LPE technology. There's more detail on this if you're interested in the recent Hot Chips presentation by Chris Berry. And as I was saying, it's really focused on generative AI to accelerate inferencing and fine-tuning workloads for enterprise customers. And it does support a variety of low-precision data formats. So this goes back to the long journey that came to this point. So we were our research team. This is IBM Research. And the journey started many years ago, and with just a proof of concept. So first we were just trying to prove basic architectural concepts independent of the technology. And then we moved to generations where we started to optimize. And then we went from sort of a one-core prototype and proof of concept to a multi-core that you can see in the bottom left. But as we went through this journey, as a research team, we created a series of these test site designs, ran them using multi vehicles through various foundries or through the foundry, just to prove these basic concepts. So one thing is we were really good at innovating on the AI core, trying new things and seeing if that would speed up. But one thing that I'll mention here is that what we didn't have was high-speed I/O. So we would create these test vehicles, we could do the proofs of concept, but we could not really do this thing at speed because we didn't have high-speed I/O, and that's obviously something that's expensive to buy, and it's something that's expensive to implement. So what we did have were custom on-chip and off-chip test infrastructures used to demonstrate the design, but we can't really create a performant object because we don't have the matching speeds of the I/O. So looking at this and going back to our experience in doing this, we want to say, well, what next? So the artificial intelligence unit today is this large monolithic system on a chip. It's a complex SoC which has both IP related to the compute, but also a lot of IP that is related to the I/O. And this was, as I said, many years in development. Looking towards the future, where do we see that? We see that in chiplets, and chiplets on a system and package. This is much more of a modular approach, which would leverage reuse and decrease our development times. So we have to start thinking about, well, we've got an SoC. What do we do with it? So this has led to a lot of thinking and work on our part to ask the question of what is chiplet factoring? So we certainly have compute cores. That's definitely something we'd want to put on our compute chiplet. But we also have proprietary elements to do things like service functions. That's probably hard to implement on a general purpose type of I/O chiplet. So that's something else we might want to think about, whether we want to keep it on our compute chiplet or offload it to another one. There's also process elements on there, because AI is not just about AI compute, it's also about doing some more processing. That would be a nice thing to potentially offload to another chiplet that might exist in the ecosystem. Some of those service functions could also be offloaded, but very, very particularly, many of the big I/O components, such as memory controllers and PCIe, are things that we don't want to have to keep re-implementing on our chip. So those would be desirable things to put in what we call Nest chiplets. So what are some of the key benefits that we might get if we're able to reuse and leverage some of these other chiplets if they existed in the ecosystem? Of course, there's lower cost. That's from faster development times and reuse of chiplets again and again. Modularity, because now that we've created a smaller unit for our compute chiplet, we can create variants of this that are right-sized for a particular application. The technology node could be optimized for each of the functions. So for example, we might want to keep spinning out our compute in the latest nodes and leveraging that, but the I/O is not necessarily constrained to be in the latest node. And then there's the potential to break this kind of reticle size limit that was talked about in the last talk. So there's a potential for higher compute per unit volume and lower communication power, because if we can bring the chiplets closer together and have more compute on a module, then we don't necessarily have to go off package or from a card to a card, which can be energetically very expensive. So to kind of summarize our approach, starting from a baseline design point, we want to achieve scale-up solutions with fast development times and leverage the reuse of existing components. But the other part of this is that we'd also like to look for derivative solutions. So can we now create new designs which would target different application spaces without necessarily having to invest that much NRE for every component? So this was a chart I shared at an earlier OCP workshop, and it just summarizes our chiplet plan. So potentially, as a product, IBM Research is designing an AIU chiplet accelerator. And this time, because this is a smaller form factor, and we want to look at the ability to go into new areas, we would be targeting an edge application. The target customer would be edge computing partners, benefiting from the capability of having a smaller form factor AI chiplet. The status is we are currently in the design phase for this. And I summarized the business issues by dividing them into what I call dating, which is exploring the compatibility of this AIU chiplet with other chiplets that might be potentially interested in it. And then a more final step, or marrying, which is packaging the AIU chiplet and bringing it up for a targeted application. So here you see just an exemplar type of configuration in which we've been able to combine our AI chiplet through a management chiplet with other third-party chiplets to create a new targeted architecture. As an example application, one of them is looking at a millimeter wave type of application, or what we call antennas to AI. We see a lot of driving forces in the market for this type of application. These include the availability of complex silicon-based millimeter wave multi-antenna systems, a large growth in the demand for infrastructure for ubiquitous communicating and sensing, and the real advances in AI capabilities, which are then used to interpret much of the millimeter wave data, which is notoriously hard to actually interpret without these types of AI algorithms. So the goal here is an AI-driven adaptation and data interpretation in commercial and DoD communications and sensing workloads. And the approach is this kind of modular chiplet architecture, which would integrate RF, mixed signal, and digital ICs. And you can see this kind of a platform in this picture. On the left is the front end, which is analog-based, an antenna array, a frequency conversion, and a beamformer. And then on the right, you see a digital platform, which might include elements like a DSP, an AI accelerator that we were talking about, and then a PHY, which goes off to the outside world. And one of the benefits of having a platform like this is that if these components exist, we can go in and any other party can go in and innovate on any one of the components and reuse the other ones. So we really like this kind of a modular approach that becomes an open kind of platform where others can innovate and improve on certain parts of the platform and leverage other existing elements. So let me talk about a little bit about some of the challenges that we've been facing and encountering, and that's why we thought that the OCP would be a very appropriate place to talk about this. The first is really the need for simulation tools to guide towards an optimal chiplet configuration. So unfortunately, you can try going into ChatGPT, saying, please tell me what is an optimal architecture for what I want to do. You probably won't get a very sensible result. You can start looking for services like maybe an eHarmony or something that might pair you with another chiplet that might be out there that's also looking for a partner. That's not yet quite reached the stage of what we want. So, having more of these architectural type tools in which you could model and implement your chiplet with other chiplets potentially in the ecosystem, and then look at how the architectures would evolve and the kinds of results and performance and power that they would give. These could also help you answer questions like, do I need one of my chiplets, or could I use, say, two of my chiplets? What would the performance difference be? They might also help you explore key packaging questions. For example, if I had standard packaging versus advanced packaging, how much benefit would I see, and what would the cost difference be? So a second one, which I think has been brought up a lot in this forum already, is compatibility. So we might be designing to a certain open standard, a bunch of wires or UCIe. You might be designing to a certain standard. We might think that we have the same standards, but are we really interoperable? I think there's a lot that has to happen above the PHY layers in terms of the handshaking, the protocols, to really ensure that if you and I independently create chiplets to the same open standard, will they really be able to communicate with each other? And then a third problem, which I'd like to highlight, is the validation. So what? So we take a very bold step. We decide we're going to go out and we're going to create a chiplet with a certain interface. And then we're thinking about other potential partners. How do I even validate my chiplet? I could put two of my chiplets on the same package, but there really isn't yet a very established methodology to say that I've created a chiplet. How can I just validate it in isolation? Then come some more mature problems down the road. We talked about the test and validation strategies. I mean, ideally, both chiplets are available and available at the same time, but you may have to evaluate them in isolation, and that just may become a part of the requirement of bringing it up. And of course, the challenges with advanced packaging of fine pitch testing. That's sort of a chiplet availability problem. A second problem that we are looking into and have been thinking about is the packaging availability for advanced pitch options. There's a lack of an open framework for package development, for prototype designs, really no MPWs, which would support the idea of getting chiplets from multi-sources, large body sizes, high densities of connections, low cost, and manufacturing in different geographies. So I want to just emphasize that we recognize that this is really an ecosystem that needs to be built, and there are many complex parts of this ecosystem. As IBM, we're very heavily invested in making this ecosystem work in all of these various aspects. At the top, you see advanced packaging and assembly capability, which IBM has onshore facilities for, and that's something that we want to leverage with this, but also create an ecosystem around it with other chiplet partners. Test and known good die methodology, EDA and co-design, interface standards, which I had discussed before. Security is obviously also a very key component of these chiplet architectures, and a secure supply chain. So with that, I'll just close with this, and we think that there's a tremendous opportunity here in the AI area, as was also discussed in the last talk. AI has very demanding compute, memory, and connectivity requirements, which can be addressed through chiplet types of architectures, and that will really open up, we think, the possibilities for applications across many different domains. So I will close with that. Oh, sorry, I won't close with that. I forgot the most important chart, the call for action.
Very important.
So this is in the template form, problems potentially to solve, protocol layer standardization, low-cost packaging solutions for integrating multi-source chiplets, so MPW type runs, but now with packaging, test, known good die, and verification strategies. And then I've put a few links here to the IBM Spire, the IBM AIU, our artificial intelligence unit, and our recent blog on chiplets. So with that, I will close. Thank you.
Question, Arvind, great talk. Would you consider opening some of those third-party requirements to the community so folks here, at least participating, can think about it?
Absolutely. That was a large incentive for why we wanted to make this presentation, that we are not in this game alone, and we would like to partner with others who have potential solutions for these.
Okay, so should we start a new work stream?
Sure.
In your dating process, which is just feasibility of
Yeah.
third-party chiplets, you made the statement that even if you and the vendor have the same PHY, doesn't mean they're compatible.
Correct.
So in your conversations, has it been more of, okay, we just get them to customize it to something that mates with ours, or is that the direction things will go in for now?
That's a good question. We've had a variety of these kinds of discussions. Some of them are, well, you tell us what you want, or what are you planning to do, and we'll see if we can implement it. And others of them are a little bit farther along and said, well, we've already established a certain protocol or a certain way of doing something, so you would need to implement that on your chip. Now, that obviously puts a burden on us as to, we're not going to design then, if we want to have a little more universal compatibility, you can't just design one thing. You have to say, well, I got to have a little bit of a flexibility that if I want to mate with, chiplet A,
Something
I've got to do
else,
it this way.
Yeah.
If I, down the line, want to mate with chiplet B, I may have to think about it a little bit differently.
Right. Yeah. Okay. No, just wanted to understand your point of view, how
Yeah.
this was going. I love the idea of the bullet number 2, the low-cost packaging solutions and MPW run. So, we've got Bill Chen from ASC. I think we've got to talk about how to make this possible for multiple players.
Right.
Because the concept doesn't exist today, but it's a great idea. Thank you, Arvind. Thank you so much for the talk.